Hello everyone, I'm honored to have been invited to speak at this conference. My topic is polynomial reproducing kernel-based image reconstruction for ECT. I'd like to share with you some of our interesting research on ECT. The content of this representation is divided into 5 parts. Firstly, we have an introduction of ECT in section 1 and describe the basic principle of the ECT system in section 2. And then in section 3, the proposed method is given. At last, based on some simulation results, we make a brief summary in section 4 and section 5. Electrical capacitance tomography is one of an electrical tomography technique which is used in industrial process monitoring. ECT is a new technology applied to multi-phase flow parameter detection, which can measure the material distribution of different dielectric constants. ECT has many advantages, such as fast response, non-intrusive, good security, and simple structure. The research of image reconstruction is a hot research field in recent years. A variety of image reconstruction algorithms has been proposed. The LBP algorithm is the most basic and direct algorithm for ECT reconstruction, but the image accuracy is not enough. The Landweber algorithm can reconstruct a better image and obtain clear image edges, but Landweber uses the gradient descent method. Step size parameter problem may lead to local convergence. The quality of the image reconstructed by TR algorithm has been greatly improved in the measurement center area, since this algorithm sacrifices a part of pixels in the iteration process. The image quality of this algorithm will become worse. So in this paper, we propose a new ECT image reconstruction method based on polynomial reproducing kernel to improve the imaging accuracy. The ECT system consists of sensor array, projection data acquisition system, and imaging signal processing computer. The forward problem of ECT is to calculate the capacitance value of each electrode plate in the ECT system under the condition that distribution of the dielectric constant in the measured area is known. We can use Maxwell's equation to describe the electromagnetic field. The sensitivity field is quickly calculated by the potential distribution method. The sensitivity matrix is calculated by calculating the variation of the potential in the measured region when the I and J electrodes and when the I and J electrodes are excitation electrodes respectively. The inverse problem belongs to the solution of ECT imaging problem. For the reconstruction of ECT image, firstly, we need to obtain the known capacitance value, and then we get the sensitivity matrix of the sensitive field through simulation. Finally, we calculate the distribution of the dielectric constant of the medium in the measured area. The relationship between the dielectric constant and the capacitance vector can be expressed as follows. The above formula can be written into matrix form. In this section, what we need to do is feature extraction. Firstly, we use an approximate solution to carry out FI modeling. The grayscale value is a direct pulse sequence signal, so we model the approximate solution as a typical FI signal. Secondly, in the FI sampling system, the FI signal is filtered by polynomial reproducing kernel and uniformly sampled. Subsequently, measurements are calculated from the samples to obtain observational feature information. Polynomial reproducing kernel can be written as this formula, and the coefficients can be expressed as this formula. Now we use this kernel to filter the FI signal, and then we sample it to extract polynomial feature information. In this way, we can get k sample values. This picture is the classical FI sampling structure, and filtering and sampling process can be simplified to the following formula. Thirdly, the measurement values can be obtained by the following formula. We can write this formula into the form of matrix. There was not enough information in the original signal. We have extracted the feature information, so we can combine the data, namely the two observation equations can be combined to get a new observation equation. The new observation equation after data fusion can be simplified to the following formula. In the ECT system, the number of pixels is much larger than the number of capacitance values obtained, which leads to the airport problem of ECT image reconstruction and instability of the solution of ECT inverse problem. It results in a low sampling rate, which ultimately reduces reconstruction accuracy. A new observation equation is constructed by zero vector filling and random recombination of row vectors. Finally, signal sparsity can meet reconstruction requirement, but the signal is not sparse enough in ECT system. Therefore, the input signal needs to be converted into sparse signal. The original signal can be transformed as follows. After orthogonal transformation, the signal becomes sparse. The sparse solution is usually obtained by solving the L-line norm optimization problem. In this paper, we use orthogonal matching pursuit algorithm to solving this problem. So the estimation of the original image signal can be obtained. In order to verify the performance of the proposed method in this paper, the simulation model is carried out. The numerical simulation model was established with console software. When the excitation voltage is applied to the excitation electrode, the potential L-square of the measured area is shown in the figure. This table shows the reconstructed image of the 4 flow patterns under the different algorithms. It can be seen from the results that reconstructed image of this method is the closest to the original image. In order to analyze the image reconstruction quality of the proposed method, we choose to use relative error and correlation coefficients as performance indexes. Table 2 and Table 3 is the reconstruction image relative errors and correlation coefficients of different algorithms. The performance indexes of the proposed algorithm are better than other algorithms. So this method has high precision. The curves of image relative errors and correlation coefficients of different algorithms are shown in the figure 4 and figure 5. Image reconstruction technology is the key to the application of capacitance imaging in this paper. An ECT image reconstruction method based on polynomial reproducing kernel is proposed to improve the image reconstruction accuracy. Firstly, the approximate solution is modeled as an FI signal, and we extract the feature information. Then, a new observation equation was constructed to solve the L-link norm optimization problem to reconstruct ECT images. The simulation results has shown that the proposed method can reconstruct better images. Therefore, the proposed method is effective. On the whole, this method has a high precision of image reconstruction, and it is worth further study. Thank you for watching.